All right, let's dive right into the world of organic chemistry, specifically to talk about carbonyl compounds. Now, these things are everywhere, but we're going to focus on two big ones, aldehydes and ketones. They look so similar you could almost call them twins, but chemically, they act in completely different, really fascinating ways. Let's get into it. So here's the plan. We'll start with the basics. What makes these molecules tick? Then we'll see what happens when we try to reduce them and oxidize them. After that, the fun part. We'll build a kind of chemical detective kit to tell them apart. Use it to solve a real chemical mystery. And then wrap it all up with a handy toolkit that summarizes everything we've learned.
Okay, so first things first, what are we actually talking about when we say aldehydes and ketones? Well, it all boils down to one single atom that makes all the difference. Take a look here. They both share that same core feature, a carbon atom double bonded to an oxygen. That's the carbonyl group. But look really closely at the aldehyde. See that hydrogen atom? It's attached directly to the carbonyl carbon. Ketones don't have that. And that one little hydrogen atom, that's the whole story. It's a weak spot, an Achilles heel that makes aldehydes way more reactive, especially to oxidation, in a way that ketones just aren't. So let's start with a reaction where they're kind of similar, reduction. This is basically where we either add hydrogen atoms to that carbonyl group, or if we get really aggressive, we just rip the oxygen off entirely. So when we use a pretty standard reducing agent, something like sodium borohydride, that C-double-O double bond breaks and becomes an alcohol. But check out the products. An aldehyde will always form a primary alcohol. That means the carbon with the OH group is only attached to one other carbon. A ketone, though, it forms a secondary alcohol. So even when they react the same way, you still get different results. But what if we want to do something more extreme, like get rid of that oxygen altogether? Well, for that, we've got a couple of heavy hitters. Both the Clemmensen and the Wolff-Kishner reductions will take that C-double-band-O group and just completely erase it, turning it into a CH2 group. The carbonyl becomes a simple hydrocarbon. It's a total makeover. So you've got two ways to do this. How do you choose? Well, it all comes down to what else is on your molecule. The Clemmensen reduction happens in a super acidic environment. If you have anything else on your molecule that might get destroyed by acid, that's a no-go. That's when you turn to Wolff-Kishner. It uses a strong base, so it's the perfect choice if your molecule is acid-sensitive. Two totally different paths to get to the exact same place. And now we get to the main event, the Great Divide, because while they're kind of similar with reduction, when it comes to oxidation, they are worlds apart. This is where their family resemblance ends, and they go their separate ways. And this image just says it all, doesn't it? For an aldehyde, oxidation is an easy path. Remember that little hydrogen atom? It's easy to break that bond and swap in an oxygen, turning the aldehyde into a carboxylic acid. No sweat. Ketones, on the other hand, put up a blockade. To oxidize them, you'd have to break a super strong carbon-carbon bond, and under mild conditions, they just refuse. If you really want to force a ketone to oxidize, you have to bring out the big guns. We're talking harsh chemicals, high heat, the whole 9 yards. And even then, it's not a pretty reaction. It's so violent that it literally shatters the molecule's carbon skeleton, breaking it into a messy jumble of smaller carboxylic acids. It's not chemistry, it's chemical brute force. Now, this massive difference in how they oxidize isn't just an interesting fact. It's incredibly useful. It's the whole basis for our chemical detective kit, a set of simple visual tests we can use to figure out exactly what we're looking at. First up, we have the famous Tullin's test, also known as the silver mirror test. Here's the deal. The reagent has silver ions floating in it. If there's an aldehyde around, it gets oxidized, and in return, it gives electrons to the silver ions, turning them into pure, solid silver. And that silver coats the inside of the test tube, creating this beautiful mirror. You see a mirror, you've got an aldehyde. Ketones, nothing happens. Next in the kit is Fehling's test. This one uses blue copper ions. Same principle. The aldehyde gets oxidized, and it reduces the blue copper ions to copper-1 oxide, which is this really distinct reddish-brown solid that crashes out of the solution. But, and this is a really important clue, aromatic aldehydes, the ones attached to a benzene ring, are too stable to react. So if this test fails, it might not mean you don't have an aldehyde. It might mean you have a specific kind of aldehyde. And our last tool is the iodoform test. This one is super specific, like a heat-seeking missile. It's not just looking for any ketone, it's looking for one very specific structure, a methyl group, a CH3, sitting right next to that carbonyl carbon.
If that structure is there, the reaction produces iodoform, which is this bright, unmistakable yellow solid. See that yellow precipitate? It's a dead giveaway you've got a methyl ketone. Okay, our detective kit is ready to go, so let's put it to the test with a real mystery. We've got an unknown compound, and all we know is its molecular formula is C8H8O. Our mission is to use these tests as clues to figure out exactly what it is. So here's our case file. We've got the formula, C8H8O, and over on the right, you can see the results from all our lab tests. Each one of these is a piece of the puzzle. Let's start putting it together. All right, first step. The unknown reacts with something called 2,4-DNP. Now, that's just a general screening test for a carbonyl group, so we know it's either an aldehyde or a ketone. Okay, next clue. It gives a negative result on both the Tollens and Fellings tests. Since those are a go-to test for aldehydes, we can say with confidence it's not an aldehyde. So our first big deduction is made. It has to be a ketone. Let's keep going. Clue number 3, we get a positive iodoform test. Remember that telltale yellow solid? That means it isn't just any ketone, it has to be a methyl ketone. So we know a CH3 group is attached right to that carbonyl. Okay, last clue. That formula, C8H8O, tells us the molecule is missing a lot of hydrogen atoms compared to a simple chain. But it doesn't react with bromine water, which is how we test for normal double bonds. So where is all that unsaturation coming from? It pretty much has to be from a super stable aromatic ring. And now for the big reveal. We put all the clues together. It's a ketone, it's a methyl ketone, and it's got an aromatic ring. There is only one structure in the world that fits all that evidence, and that is acetophenone. It matches the formula, it's got the aromatic ring, and it has that methyl ketone group that gave us the positive iodoform test. Case closed.
Wow, okay, that was a lot to take in. So let's just pause for a second and boil everything down into a simple, clear toolkit that you can use as a reference.
And here it is. This table is basically your cheat sheet. You can see the pattern so clearly here, right? For anything involving mild oxidation, Tollens, Fellings, the aldehyde is reactive, the ketone is not. For the super-specific iodoform test, only that methyl ketone structure gives a thumbs up. And even when they both react, like with strong reduction, they still give different products. This is everything you need to know. So we'll end with this thought. We just saw how one single hydrogen atom completely changes the fate of a molecule, creating this huge chemical divide. It really makes you think, doesn't it? What other tiny, almost invisible changes in a molecule's structure are out there, just waiting to be discovered, creating completely new properties and reactions we haven't even dreamed of yet? Thanks for watching.